So, now based on the type of circuit element that you have that defines your material. Please remember, you do not have a predefined notion of a circuit for your material. You need to do the test for your material, get the Nyquist plot for your material, and then idealize the material behavior in terms of an equivalent electrical circuit. For example, if you only get one point here for your material, that means it is only a resistor. Okay. So, you can approximate an equivalent circuit of just a resistor in your material. Okay. So, if your point is not changing with respect to frequency, that means your current and potential are in phase and you are not going to get any change in the impedance. So, you will have an exact value which is again typical of your direct current measurements. Okay. Now, but the problem with direct current measurement is you will not get exactly this value because there will be a polarization potential that is against the applied electric field. So, you will not exactly get this value, right, but this is the true value that you want to actually use for your real resistance, right. So, you get that concept. So, we are testing any material which conducts and doing the Nyquist plot for that material and idealizing the Nyquist plot using an equivalent electrical circuit to get the actual electrical performance or actual electrical properties. So, again, so impedance, as I said, Z is directly equal to R. In the case of a pure inductor, Z is given as J omega L, and as I said, it is shifted or it is lagging the potential. So, it is minus 90 out of phase, minus 90 degrees out of phase with the potential. And what happens with increasing frequency is that the inductance value will increase. The capacitance on the other hand is given as 1 divided by j omega c, and basically this decreases. Okay. With increasing frequency, the capacitance or impedance for a pure capacitor will decrease, because obviously your omega is in the denominator, here omega is in the numerator. So, it is a direct relationship for the impedance with respect to the frequency. For a pure inductor, the impedance increases with increasing frequency, and for a pure capacitor, the impedance decreases with increasing frequency. So, as I said again, what you need to do is have these three basic elements and draw your own equivalent circuit for what you think best represents the electrical behavior of your system. Okay. So, for example, you can have a resistor and a capacitor in parallel. So, that could be one of the representations of the kind of material that you are investigating, right. You may get other systems also with an inductor, with a capacitor and inductor, and so on and so forth. There are a lot of systems that conduct in different ways. Okay. For the most part, we use this sort of a relationship to describe the situations in which you have steel embedded in concrete. Okay. And I will show you why that happens, because generally when you have steel which is embedded in an electrolyte like concrete or an electrolyte like a pore solution, for instance, you get the simplified Randall cell which approximates quite well the behavior of the steel embedded inside concrete or an electrolyte. So, what are these three components? You have a resistor component outside, and then you have a resistance and capacitance in parallel. How is this arising? You have the double layer capacitance basically, which is on the surface, right, on the surface of the steel where it is in contact with the electrolyte. You have what is known as double layer capacitance. So, your ability to actually store charge is high at the interface. You then have the electron transfer resistance, which is between the steel and the surrounding electrolyte, and you also have an uncompensated or electrolyte bulk resistance of the electrolyte, which is outside. Okay. So, whenever you have interfaces in materials, electrochemical impedance spectroscopy can actually help to bring out the characteristics of the interface quite clearly. And when you actually go through the presentation by Sripriya, you will know how this can be actually used to study the properties of the steel concrete interface and make some valid conclusions about when corrosion begins in concrete when steel is embedded in it. Okay. But for now what we will do is we will use a very simplified approach of the impedance data and see how it works to explain the pore structure characteristics of concrete. Okay. So, as I said again, the imaginary negative of the imaginary part is plotted on the y axis and positive of the real part is plotted on the x axis, and the point at which this arc touches the x axis equals the actual DC resistance of your structural component or of your concrete, for instance. Okay. Now, again, when you get an impedance data which is looking like this, what we typically say is this part which is going up at around 45 degrees is because of the response of the electrode, okay, whereas this arc that you get here is the response of the material that you are actually testing when you are testing concrete, for instance. Okay. So, what do we get from this as a result of this test is the value of the DC resistance R, and this R can be converted into the resistivity rho by multiplying by A and dividing by L. Alternatively, it can be used to determine the conductivity as L by Ra. Okay. So, all we are doing is taking inverse of resistivity and expressing as conductivity. So, you can represent the data in both ways, either as conductivity or as resistivity. So, let us look at how this is used in materials research. So, one of the common methods which we apply both in soils and in concrete is the determination of the resistivity of the material. Now, we use electrical impedance to study the evolving structure of concrete, because as the concrete structure evolves, the pores become more and more disconnected. When pores get more disconnected, what happens to the resistivity? It will increase. So, you can measure electrical properties using impedance and track the development of your pore network, or increasing disconnectedness of your pore network can be detected. So, here for instance, a typical measurement is done using a 4 probe technique, which is also known as a Venner 4 probe technique, okay, which previously was determined or developed for measuring soil resistivity characteristics. And what is done here, you have an AC current source which is supplying current to 2 outer electrodes, and you also have 2 inner electrodes in this system across which you actually measure the potential difference. You apply an electrical current and you measure the potential, and from the measured potential, right, you convert the value to an equivalent resistivity of the system. Okay. Now, there are several scales for what the resistivity actually denotes. For example, in the case of soil corrosiveness classification from British Standards 1337, it says that if the soil has a resistivity of 100 ohm meter or more, it is only slightly corrosive. That means it is not really having a characteristic that will be harmful. Okay. Between 50 and 100, it is moderately corrosive. As you become lesser and less in resistivity, the corrosion or corrosive nature of the soil gets enhanced. Now, what is causing this corrosive nature of the soil? Obviously, the presence of ionic species in the soil, right, like sulfates, chlorides, for instance, right. So, all those ionic species are contributing to reducing the resistivity or increasing the conductivity of the soil for a given porosity present in the soil. Now, if you take the soil and you compact it by vibration compaction, what do you think will happen to the resistivity value? Resistivity will increase, because more compact soil implies you have lesser porosity, automatically you get lesser interconnected porosity. So, your resistivity obviously will go up as you compact the soil more and more. Okay. Now, the same concept applies in concrete also, but in concrete we have 2 different methods or 2 different configurations. One is the uniaxial configuration, which is used in bulk conductivity measurements, or we have the same Venner 4 probe surface resistivity test. Okay. Now, bulk conductivity we say because we take concrete specimens and we have the positive and negative electrodes directly attached to the ends of the concrete specimen, like a cylinder for instance, and then we simply measure the bulk electrical response when we apply alternating current. Okay. So, here for instance your length is clearly defined, right, your area across which the current is passing is also clearly defined because you have a perfect cylindrical specimen, right. So, you get your resistance as rho multiplied by L divided by A. So, here you can have a generic relationship between your resistivity rho and the resistance R by a factor K. Now, in this case of course your K is very simple because your path of flow is perfectly maintained, your path of flow of the electric charge is perfectly maintained. So, you have this K represented just as the area divided by the length, okay, it is the same relationship rho equal to R A by L. In the case of surface resistivity test, it is a little bit more complicated because while you are applying an electrical current across the two outer electrodes, you are trying to measure the potential drop across the two inner electrodes. And again I will come back to this picture later. So, if you look at the more detailed drawing of this resistivity, so again these are the 4 probes that are sitting directly in contact with the surface. The distance between the probes is constant A. Okay, in all the cases you have the constant distance between the probes A. Now, if you look at the lines of current flow, they are defined by these isoplets that are drawn in this figure. However, the equipotential lines are what are emanating from the source of the current. Okay. So, where the equipotential lines define the potential at this point and this point, okay, that is what we are trying to measure using the potentiometer between the or potentiostat between the two inner probes, and that we are using to calculate the resistivity in terms of this equation 2 pi A V divided by I. Now, what is V by I? That is nothing but R, but where did this 2 pi A come from? It comes from this expression here that I showed you previously. For resistivity of concrete systems, rho is given as K times R. K is the geometric correction factor which we need to apply in this case. It is a little bit more complicated than what we had in the case of the bulk conductivity experiment where the path of flow is perfect. In this case we need to consider the effect of the size of the specimen and the spacing between the electrodes. We need to consider the effect of size of specimen and spacing between the electrodes. Now, what happens is generally we apply this to systems where the size of the specimen is much larger as compared to spacing between electrodes. So, when you apply this to this equation, what will happen? D by A will be very large number because D is very large compared to A. So, in other words, this entire thing will go up to about 1. That is why we have a numerator typically used for calculation as simply 2 pi times A. Now, you need to remember that very often we do not really conduct the experiment on infinite or rather very large thickness. We have specimens that have finite thicknesses. So, you may actually have effects built in because of those finite thicknesses, which is why we need to use specimen sizes which are at least 3 to 4 times the spacing between the electrodes. Okay. So, the commonly available instruments that you get from the field from the commercially available instruments that you get have a spacing A of 38 millimeters or 50 millimeters typically. So, if you say 38 multiplied by 4, you are talking about a minimum diameter which is or minimum size which is at least 150 mm, or at least the length of flow should be 150 mm. Some in one direction at least you should have a spread that is equal to about 150 mm. Okay. So, when you start using this resistivity test on smaller specimens, you need to take the result with a pinch of salt. It is not perfect when you take it on small specimens. When you measure on a very large block of concrete, you can be fairly certain that your calculation, which is given as this 2 pi 8 times V divided by I, will be more or less accurate for a very large block. The smaller the specimen, you have a problem. So, of course, this assumes uniform current distribution throughout the electrolyte area in the cover zone of the concrete. Why are we worried only about the cover zone? because when we are actually placing this resistivity probe on top of the concrete surface, the current flow is actually happening only in the cover zone of the concrete. We are not getting any current flow in the bulk of the concrete. That is why the name surface resistivity, we call it surface resistivity, whereas in this case we call it bulk conductivity or bulk resistivity. I do not exactly remember the standard number, but it is ASTM C1760, I think. You can actually refer to the standard and check for yourself. It is the bulk conductivity determination standard, and it is quite commonly used these days as a good durability parameter that can be measured fairly easily. Okay, you need only few minutes to do this test. Before your strength determination on cylinders, you can determine the bulk conductivity and then determine the strength. Okay, so very useful test to do for regular quality control purposes also. However, given the fact that the Venner probe can also be used in the field, people generally tend to have this equipment quite handy in most labs, and because of that it is quite useful to actually conduct the conductivity or resistivity determination with the Venner 4 probe equipment also. One major issue is the presence of moisture in the concrete. You have to remember that when you are doing laboratory investigations using resistivity, you need to make sure that all your samples or all your specimens are completely saturated, because when you have drying, it can play havoc with the kind of data that you can obtain from resistivity measurements. For moist concrete, 10 to the power 4 ohm centimeter, and for oven dry concrete 10 to the power 11 ohm centimeter. So, that is absolutely not comparable. You have 7 orders of magnitude difference in the resistivity data. So, use of this resistivity probe on site needs to be done with a lot of care, because if you cannot ensure that your surface that you are measuring the resistivity on is completely moist, or if you can determine the moisture content there, you should report it for that moisture content. Okay. But on site you need to contend with one more problem. There is going to be steel under the surface, and very often the current flow lines can actually end up intercepting the steel also, in which case you will get completely erroneous readings. You want to check the conductivity of the concrete or resistivity of the concrete, not the entire system. Okay. So, the presence of steel will obviously lead to errors in field measurements, but more than that is the presence of moisture, which plays havoc with the measurement of resistivity in concrete systems. But anyway, what we will do in the next part of this lecture is look at how this is applied to do various kinds of research studies. But before that, I just wanted to talk about the guidelines that are typically used for resistivity to define the performance of concrete in the event of corrosion. Generally, it is well understood that more resistive the concrete, the more resistance it will offer to the passage of ionic species within it. That means the ionic flow will be restricted in concrete that is highly resistive, and you know very well that corrosion propagation generally happens when you have ionic flow happening through the concrete. Basically, your Fe2 plus and OH minus ions move through the concrete, and any resistance to the movement of those ions will result in better performance as far as corrosion is concerned. So, generally the corrosion related criteria are drawn up based on resistivity in this fashion. For example, one of the characteristics, one of the versions says that if you have a resistivity of concrete more than 12,000 ohm centimeter, corrosion is unlikely. Between 5,000 and 12,000 it is probable, and less than 5,000 you are certain to have corrosion in your system. There are other versions also in use. I will show you an example of ACI 222R. I think this is the committee that deals with corrosion or corrosion inhibiting admixtures. So, ACI 222R report says that again for 5 you have a very high corrosion rate. These are in kilo ohm centimeter, right. So, it is the same as this 5,000 ohm centimeter. So, less than 5 your corrosion rate is very high, 5 to 10 it is high, 10 to 20 is low to moderate, and greater than 20 is low. But a more sophisticated model is proposed by the Florida Department of Transportation in their document FM 578, which says that resistivity values of less than 12 indicate a high risk of chloride ingress. Now, please remember that your resistivity is in no way linked to the actual physical ingress of the chlorides, right. Your resistivity is just defining the interconnectivity of the pores. But you all know very well that the more interconnected the porosity, the greater the risk of ionic species coming in from the outside. So, again there are various ways in which the data is interpreted, and none of these can be entirely accurate, right. So, what this says is for 12 it is high, or less than 12 it is high, 12 to 21 is moderate, 21 to 37 is low, 37 to 254 is very low. Okay. Now, of course, where did these numbers come from? These came from a very large data set of testing, which they were able to actually get these values from, to see how the resistivity is actually matched with the actual corrosion potentials in these concretes. Again, this is another picture from an ASTM special technical publication, which looks at the corrosion current plotted on the y axis versus resistivity of the concrete in kilo ohm centimeter. What you can see very clearly is there is a distinct trend which shows that as the resistivity becomes more and more, the corrosion current in the concrete is less and less, and that is only expected because the higher the resistance, the greater will be the potential to resist the charge flow through the concrete. Okay. So, because of that, the corrosion charge or corrosion current reduces with increasing values of resistivity. Now, generally when we do corrosion studies, this 0.1 microampere per centimeter square corrosion current density is said to be a critical value of density, which defines the state of passive corrosion and active corrosion. Anything more than 0.1 indicates active corrosion in your system. Okay. So, you can see that for levels of resistivity which are greater than about 10 to 20, right. So, most of these values here are more than about 20 or 20 to 25, 20 to 30 for instance. Most of those concretes are in the passive condition, whereas anything which is less than 20 is mostly in the active condition. So, if you come back to this Florida Department of Transportation, more or less it matches with what we are actually seeing as far as the corrosion current density behavior is concerned. Your resistivity indicated by the experiment will get reduced when steel is present in the vicinity, because the charge is getting carried much easier, right. So, because of the presence of steel, you will actually show a lesser resistivity in your system. So, maybe you can say that that is a more conservative approach to have the steel inside. Yeah, see again we are talking about ideal situations for an electrolyte alone, like just a pore solution for instance, right. But when you are considering a solid phase which is present inside the concrete, like your aggregate or cement paste, even you have the hydrated cement paste which is a solid phase, and that will lead it to actually have an impedance. You will actually go away from the idealized resistor type of an arrangement, and you will also get some charge storage capacity. The greater the extent of solid phase, the more will be the storage capacity. So, capacitance will play a larger role in the case of a concrete. So, I will just stop with this graph here to the right. Again, it is the same sort of a graph with corrosion rate I-core versus electrical resistivity, that is taken from actually a paper published in 2018 in a scientific report in the Nature journal. So, it is quite well cited obviously. So, here it shows you the effect of the relative humidities. As you go with lower and lower relative humidities, obviously your electrical resistivity that is shown is very high, whereas when you go with almost saturated concretes, the electrical resistivity becomes very low and your corrosion rates are much higher as the electrical resistivity reduces. So, that seems to match well with our understanding of corrosion, because corrosion rate is going to be high in a very moist environment. When the environment becomes drier and drier, your corrosion rates are not going to be as high, because there is no easy path for the flow of your charges. Okay. So, this holds a lot of importance with respect to understanding how corrosion propagates in concrete systems which have different types of binders, like if you have slag or silica fume, and the kind of resistance that offers to the actual flow of charge in your system can define to a large extent how the system will perform in a real corrosion experiment. Okay, so, in the next part of this chapter we will look at how actual data can be interpreted to make some distinct understanding of your pore structure and whether that representation of the electrical pore structure or electrical properties derived pore structure is able to accurately quantify the durability performance of concrete. Okay. Thank you.